Welcome back, Chemistry 30. This is EQ 3.7, weak acids and bases. 3.6, we saw what happens with strong acids and bases, meaning that they completely dissociate into H pluses or hydroxides. Weak bases and acids, we'll see, only partially dissociate. So that's going to involve a Ka or a Ka or Kb, equilibrium constant to see. It will be an equilibrium, how much of it exists in the product. Just very similar to what we did earlier. And get pH from that, and then calculate the pH of a weakened base, etc., etc. So we'll look at the acids first, and then the bases. So weak acids. Most acidic substances are weak acids. So previously we saw the strong acids, bases. I think there was something like 7 strong acids and a few weak bases, strong bases. But most things exist in either strong acids weak acids or weak bases. So the key thing is they only partially break down, partially ionize, partially dissociate into aqueous solutions as seen below. So if we take a look over here, if we look at a hypothetical reaction, HA, I know A is an anion that doesn't exist, but let's just say it did. You can see right off the bat there's an equilibrium. So part of it transfers its H over, so that water becomes hydronium, leaving A negative behind, and some goes back into here. Or we can look at it in terms of an acid, partially breaks down to H and A, but as you can see, since there's a reverse reaction, a lot of it exists in the undissociated form. So we can use the equilibrium constant for the ionization reaction to express to the extent to which it ionizes. If we represent the general acid HA, we can write this equation as I just mentioned there. So before with the strong acids and bases, there's just one arrow to the right because it all dissociates or ionizes into H. But here, only partially. So because H2O is the solvent, it is omitted from the equilibrium constant just like we talked about before. So we could just simply look at this part. Just simply look at the part that involves the acid ionizing into H and A minus. So H multiplied, or H plus multiply that over the undissociated form, so we get the Kc value. As we did for the ion product constant for the autoionization of water, we changed the subscript from Kc or Keq to Ka to represent the acid dissociated constant. I'm out of focus. There we go. So the acid dissociated constant, because that's what we're pertaining to over there. All right. So the subscript A denotes that Ka is the acid dissociation constant. And of course, the size of Ka, now to figure out Ka, you're basically taking, again, products over reactants. How much is in product compared to reactant? If it was a strong acid, all of it would exist in product form, but again here only partially breaking down. So the larger the Ka, the stronger the acid, because the more that exists in the ionized form. So chlorous acid, for example, is one of the strongest of the weak acids, and we can take a look here. So the strongest acid, decimal is 0.1 for a Ka. So that's, even though that's a big number in terms of acid, it seems like it's a relatively small number, so it's a weak acid. And then you can see acetic acid here, which is in vinegar, etc. So with that, we'll take a look at calculating Ka from pH, and then vice versa. In order to calculate either the Ka value for a weak acid or the pH, we use many of the skills that we solved with Kc, and that involves, of course, drawing an ice chart. In many cases, the small magnitude of Ka allows us to approximate to simplify the problem. In these calculations, it's important to realize that proton transfer reactions are generally rapid. As a result, the measure or calculating of pH for a weak acid always represents the equilibrium position or a condition. So we're going to get pH from the H value at equilibrium. So we'll take a look at these two examples. We'll look at calculating Ka from pH and then vice versa down here with this one. So a student prepared a 0.1 molar solution of formic acid and found its pH at 25 degrees C to be 2.38. Calculate the Ka. So we know an initial amount. We know that formic acid, this is what we're dealing with. And of course we assume at the very start we don't have anything else being formed. So ice, so we have 0, but then we're told we know what the pH is. Now, what we can do with the pH is we can figure out what the H is at equilibrium. So if you look back at your formula sheet, you'll see that to figure out the concentration of H+, it's equal to 10 to the negative pH. So we can in fact get what H is at equilibrium. So 10 to the negative 2.38. So make sure you use your button on your calculator. It's like an X to the Y button or a Y to the X button, 10. Or of course, if you look above your log button, you'll see that it's 10 to the X. So you'll be responsible for looking at your own calculator and figuring out. When you do type that in, you get 4.168 times 10 to the minus 3. All right, that's what we get. So from there, I'm just going to round that off to 2 sig figs. So at equilibrium, 4.2 times 10 to the minus 3. Now in this case, 1 breaks down to give 1 and 1. So I will have the same thing here. So I'm going from 0 to 4.2, so that means I must have added that amount. And that's a negative 3 here, so be careful, negative. And since this is a 1-to-1, it's the same number over here. So I went from 0 to 4.2 times 10 to the minus 3. And then 1-to-1, so if I added 4.2, I must have subtracted 4.2 times 10 to the minus 3. So 0.1. So when I subtract that, I'll get 0.0958. So there we go. I have all of my my equilibrium values. Now to figure out Ka, it's just simply products over reactants. So that's over this. So I have 4.2 times 10 to the minus 3, 4.2 times 10 to the minus 3, all over 0.0958. So plug that into your calculator, 1.8 times 10 to the minus 4. So you see that's a really small number, right? That means very little exists in this form. Most of it exists in this form. In other words, undissociated acid. So remember, the stronger the acid, the more H plus ions there are floating in solution. So if there's very little H plus ions floating around, that means it's a weaker acid. All right, vice versa. Calculate the pH of a 0.2 molar solution of HCN. Note that HCN is a weak acid and its Ka value is this. So let's say we can set this up. It's vice versa. Kind of backwards. So we have this, set up the ice. We know it's a 0.2 molar solution. We know we have 0 and 0. We know something's going to get added here. Something's going to get subtracted here because it's breaking down and going to the right. And we also know that to figure out Ka is this, products over reactants, and that's all we know. We are told what the Ka is though. Now, so in this case, we know nothing inside this chart here, but remember, very similar to what we did before. It's kind of similar to figure out molar solubility. We represent this as K. Since this is 1-to-1-to-1, whatever I use up here, I add up over here on the right-hand side. Then over here, 0.20 minus X. So that's how we can set it up. We set it up as an unknown. Ka, we know is 4.9 times 10 to the minus 10. X times X. And 0.2 minus X. Now, very similar to what we did before here. Very similar to what we did with equilibrium. Kind of a mathematical nightmare there. But here we can assume X is very small compared to 0.20. Therefore, omit it. Now, in our everyday life, 0.2 is a small number, but in terms of concentrations, 0.2 is a fairly big number here. So we can omit it. It'd be like saying $10,000 subtract a nickel. Well, that nickel's not going to make a big difference. So we can get rid of that x because 0.2 is really going to be what the denominator is. So let's move up to over here. So 4.9 times 10 to the minus 10 equal to x times x, which is x squared, over 0.2. So multiply each side by 0.2, and then square root. So multiply by 0.2, and then of course, so jumping 2 steps here, multiply by 0.2, multiply by 0.2, then of course x squared. We need to square root that side. So x is going to be equal to 9.9 times 10 to the minus 6 molar. So there we go. We know what H is. And if we know what H is, we can definitely figure out what the pH is. So here, X represents H at equilibrium, represents Cn minus at equilibrium. It also represents what I subtract from 0.2. Notice, yeah, this is small. 0.2 minus 0.000009, that's a really small number. So pH equals negative log of H plus. So pH equals negative log of 9.9 times 10 to the minus 6. And when you plug that in, you get pH equal to 5. So you can see it's slightly below 7, weak acid. All right, that's it for video 1. Video 2, we'll look at weak bases and see how we handle that.